Lesson 4. Introduction to NDT Indications. Introduction. This lesson focuses on inspection and analysis when using various NDT methods. Because of the vast number of possible indications encountered with various components from different industries, we will focus on the most commonly encountered indications. Indications. Indications are produced when testing is performed and a response or evidence thereof appears that requires interpretation to determine its significance or relevance. During interpretation, indications are classified as false, non-relevant, or relevant. False indications. False indications are produced by something other than a discontinuity. Many times a false indication arises from improper handling procedures. A false indication may be confused with or mask a relevant indication, but can be formed because a technique was misapplied or is the result of some other factor unrelated to a discontinuity, such as magnetic writing in magnetic particle testing or a smudge during liquid penetrant testing. In radiographic testing, false indications are usually referred to as artifacts. Non-relevant indications. Non-relevant indications are caused by a condition or type of discontinuity that is not rejectable. A non-relevant indication may also result from a misapplied test or may be an indication that is too small to be considered relevant. Non-relevant indications usually result from intentional interruptions in a part, such as a change in section geometry, thickness, or hardness, or by a physical condition that is not a discontinuity. Non-relevant indications are caused by normal or intended conditions in the part or material. Non-relevant indications are predictable, and the inspector should be able to identify their cause. Some common part configurations that result in non-relevant indications are sharp corners, keyways, splines, abrupt changing in section thickness, and threads. Both non-relevant and false indications are types of indications that have no bearing on the integrity or soundness of the part or component that is being tested. However, they should still be evaluated as they could hide relevant indications. Relevant indications. Relevant indications are the result of an actual unintended discontinuity that must be reproducible and evaluated against a set of acceptance criteria to determine the severity of the discontinuity and disposition decision. Finding and evaluating relevant discontinuities or indications at an early stage is a critical step in preventing discontinuities from becoming more serious and causing failure during subsequent processing or while in service. Discontinuities. A discontinuity is an intentional or unintentional interruption in the physical structure or configuration of a part. As part of the NDT process, evaluation criteria are applied to determine if the discontinuities that are discovered may or may not affect the usefulness of the part. A discontinuity is classified as a defect when it falls outside of acceptance limits. As a reminder, all defects are discontinuities, however, not all discontinuities are considered defects. Discontinuities are classified into 4 categories. 1. Inherent discontinuities, which originate from the solidification of cast or molten metal. Inherent discontinuities may also have their origin in other bulk consolidation techniques, such as press and sinter, as well as composites. 2. Primary processing discontinuities, which arise from the hot or cold working of an ingot into forging, rod, bar, pipe, tube, and welding. As well as inherent discontinuities, primary processing discontinuities may be found in composite materials. 3. Secondary processing discontinuities, which stem from secondary processing and finishing operations such as machining, grinding, heat treatment, and plating. 4. In-service discontinuities, which are caused during the use of the part. Inherent discontinuities. This group of discontinuities occurs during the initial melting and refining processes, such as with ingots, and during solidification from the molten state in castings. Such discontinuities are present before rolling or forging is performed to produce intermediate shapes. The most common inherent discontinuities are blowholes and porosity, cold shuts, hot tears, shrinkage, also known as microshrinkage, shrinkage cracks, non-metallic or slag inclusions, and pipe. Blowholes and porosity. These are surface and or subsurface discontinuities which are spherical in shape, and they occur primarily in the casting process. As molten steel is poured into a casting mold and solidification begins, Some gases can be trapped, forming porosity or blowholes. Cold shuts. Cold shuts are surface or subsurface discontinuities found in ferromagnetic or non-ferromagnetic test objects. Cold shuts are produced during the casting of molten metal due to the cooling variations from splashing, surging, interrupted pouring, and or the meeting of two streams of metal coming from different directions which tend not to fuse together. Cold shuts generally appear as smooth indentations on the cast surface and may resemble a forging lap. Hot tears. Hot tears are surface or near-surface discontinuities found in ferromagnetic and non-ferromagnetic casting material. They're caused by non-uniform cooling, resulting in stresses that rupture the surface of a metal while its temperature is still in the brittle state. They may originate where stresses are predominant due to the rapid cooling of thin sections that adjoin heavier masses of metal, which are slower to cool. They appear as ragged lines of variable widths and numerous branches and may occur individually or in groups. Shrinkage, also known as microshrinkage. These are subsurface discontinuities found in ferromagnetic or non-ferromagnetic castings, especially with magnesium castings. They occur while the metal is in a semi-molten state. If sufficient molten metal cannot flow into different areas, the shrinkage will leave a void as it cools. Shrinkage cracks. Shrinkage cracks are surface and subsurface discontinuities found in ferromagnetic and non-ferromagnetic metal castings. Shrinkage cracks develop as a result of contraction tensile stress that occurs during metal solidification cooling process, resulting in the rupture of the metal. Shrinkage cracks are concentrated where there is a change in cross-section because thinner areas solidify and cool faster than thicker cross-sections. Shrinkage cracks are sharp, clean-cut indications that usually appear in groups. In some cases, very fine branch-like patterns can be observed. Non-metallic slag inclusions. Non-metallic inclusions are primarily subsurface discontinuities found in ferromagnetic and non-ferromagnetic ingots and castings. They are caused by oxides, sulfides, and other impurities that are entrapped in the molten metal as it solidifies. They are normally lighter than the metal, and the majority of inclusions in slag rise to the top while the metal is still in the liquid state. Most of this material is removed during cropping operations. Non-metallic inclusions, when further processed, can produce laminations, seams, and cracks in finished material. Inclusions can become stress risers in forged parts. Pipe. Pipe comprises surface and subsurface discontinuities found primarily in steel and other metals poured into ingot molds. Pipe is formed when an ingot cools more rapidly at the outside surfaces than the inside surfaces, thereby causing the formation of a central cavity as the result of the shrinkage. Primary processing discontinuities. Discontinuities can also be introduced into metals during hot or cold working of an ingot into forgings, rod bar, pipe or tube, as well as with welding operations. The most common primary processing discontinuities are rolling, forging, and extruding discontinuities, stringers, laminations, seams, and unfused porosity, and the various welding discontinuities. Convolution cracks. Convolution cracks are surface discontinuities found in non-ferromagnetic material. The rough orange peel-like effect of convolution cracking is the result of either forming operations that stretches the material or a chemical attack such as pickling treatment. The roughened surface contains small pits that form stress risers. Subsequent surface applications, such as vibration and flexing, may introduce stresses that act on these pits and form fatigue cracks. Forging laps. Forging laps are surface discontinuities found on ferromagnetic and non-ferromagnetic materials due to improper rolling, forging, or sizing operations. Forging laps appear as seams that are created by folding over hot metal, fins, or sharp corners, and then flattening them onto the surface. However, they do not always get fused into the parent metal. Forging laps appear as wavy lines and are not usually very pronounced. They also have surface openings that may have been smeared closed. Mandrel drag. Mandrel drag is embedded material, surface gouges, or ragged tears found on the inside diameter surface of ferromagnetic or non-ferromagnetic seamless tubing. Mandrel drag stems from ruptured material being forced over during piercing and subsequently being dragged by the mandrel, damaging the inner surface or depositing material in the process. Tubing cracks. Tubing cracks are surface cracks found on the inner or outer diameter of both ferromagnetic and non-ferromagnetic tubing that run parallel to the direction of the grain, not necessarily the direction of the tubing, but the direction of the grain. Tubing cracks stem from improper temperature during the annealing or processing. Bursts. Bursts are surface or subsurface discontinuities found primarily in ferromagnetic and non-ferromagnetic material that has been forged, extruded, or rolled improperly or at improper temperatures. They appear as straight or irregular cavities, varying in size from wide open to very tight, and are typically parallel with the metal grain. Cupping. During drying or extrusion processes, cupping occurs when the interior of the metal does not flow as rapidly as the surface and ruptures internally. They visually appear as chevrons. Hydrogen flake. Hydrogen flake is evidence of internal fissures on a fractured ferromagnetic material surface attributed to stresses produced by localized transformation and decreased solubility of hydrogen during cooling after hot working. Flakes are extremely thin, appear as bright silvery areas, and are generally aligned parallel with the grain in heavy steel forgings, billets, and bars. Flash line cracks or tears. Flash line cracks and tears are surface discontinuities found on ferromagnetic material due to excess metal force being extruded between the upper and lower dies during forging. This extruded metal is called flash and must be removed by trimming. Cracks and tears are evident along the trim line when caused by the improper removal of flash. Stringers, laminations, seams, and unfused porosity. These stem from material that has inherent discontinuities, usually subsurface, already present prior to primary processing. These inherent discontinuities create newly defined primary processing discontinuities. This is why NDT is so important throughout the manufacturing process. Inspecting for and screening out inferior material early in the manufacturing process will alleviate many processing discontinuities and much waste in regard to materials, time, and manpower. Stringers. Stringers are ferromagnetic and non-ferromagnetic surface discontinuities that arrive after forging, extruding, or rolling of original bar stock that had an inherent discontinuity of non-metallic inclusions. These inclusions get elongated during processing and appear as long, straight lines or stretched masses parallel to flow lines. Laminations. Laminations are surface and subsurface discontinuities that are extremely thin due to flattened impurities such as pipe, blisters, seams, inclusions, or segregations. They are found primarily in plate and sheet metal that is rolled or extruded, as well as with forgings. Seams. Seams are surface discontinuities found mostly in bar or stock that had an inherent discontinuity prior to primary processing. During primary processing of rolling, forging, or extruding, the inherent discontinuity becomes elongated into what appears as a seam line parallel to the direction of metal flow. The image we see here is of a seam that was identified using non-destructive testing, specifically magnetic particle testing. Unfused porosity. Unfused porosity comprises subsurface discontinuities found in wrought aluminum that has been rolled, forged, or extruded. Unfused porosity is attributed to porosity in the cast ingot that gets subsequently rolled, forged, or extruded and flattened into a wafer-thin shape. Welding discontinuities. Welding discontinuities can result from a number of factors including improper welding technique, electrical settings, contamination, improper joint condition, etc. Some of the more common welding discontinuities include root concavity, also known as suckback, incomplete fusion, incomplete penetration, unconsumed inserts, arc strikes, heat-affected zone cracks, drop-through, also known as burn-through, inclusions, porosity, undercut, and surface shrinkage cracking. Root concavity. A concave root surface comprises surface discontinuities found in both ferromagnetic and non-ferromagnetic welded material, commonly known as suckback due to the root having a concave appearance after cooling. The discontinuity is caused by excessive shrinkage of the weld-deposited root bead after improper welding techniques. Drop-through. This surface discontinuity in ferromagnetic and non-ferromagnetic welded material is virtually the opposite of concave root surface, where an undesirable convex sagging is evident due to excessive root bead width. Drop-through is sometimes known as convexity or excessive penetration and typically occurs when weld temperatures are too high for the base material. It stems from welder inexperience and improper welding technique. Incomplete fusion. Also referred to as lack of fusion, this weld discontinuity stems from the failure of adjacent weld metal and base metal or of weld metal and weld metal to fuse together. Incomplete fusion results when a base metal or previously deposited weld is not raised to the melting point at the point of weld deposition fusion. Inclusions. Inclusions comprise foreign material that is introduced and entrapped in ferromagnetic and non-ferromagnetic metal weld material. Inclusions can appear anywhere within the weld, meaning both surface and subsurface, and in any shape. Tungsten, oxide, and slag inclusions are common in the welds of inexperienced welders. Incomplete penetration. Incomplete penetration is also known as lack of penetration. It is found in ferromagnetic and non-ferromagnetic weldments. It's the result of the weld metal not penetrating through the entirety of the root. It's caused by improper welding travel speed, improper weld temperature, or improper weld joint fit-up. The image we see here on the right is of a double V groove weld meant to be a complete joint penetration weld, where when it was welded in the fabrication portion, they did not penetrate thoroughly through the joint, leaving a gap between the two welds. While in service, this gap between the two welds caused a fatigue crack to fail the member. Porosity. Porosity comprises surface and subsurface weld discontinuities found in ferromagnetic or non-ferromagnetic weldments caused by gas entrapment in the molten material. Gases can be released by the cooling weld metal because of reduced solubility as the temperature drops, or from gases formed by chemical reactions in the weld. Porosity is also caused by too much moisture on the base or filler metal or improper cleaning or preheating. Porosity appears as bubble voids in the solidified weld material. Unconsumed insert. Found in ferromagnetic and non-ferromagnetic welded material surfaces at the root bead, an unconsumed insert results from pre-placed filler material that is not completely melted and fused into the root weld. This condition is caused by low welding current, improper weaving procedure, improper joint design, or improper welding speed. Undercut. Undercut is found in both ferromagnetic and non-ferromagnetic welded materials. Undercut is a groove that is melted into the base metal along the edge of a weld or along the toe of the weld and left unfilled by the weld material. An undercut is the result of improper welding procedure, such as excessively high amperage or a large welding rod. Arc strikes. Arc strikes are weld discontinuities in both ferromagnetic and non-ferromagnetic materials that are situated on the surface of the base material where a welder has momentarily touched an arc welding electrode to initiate the arc, resulting in a localized arc strike area. Arc strikes often harbor minute cracks, porosity, and hardness variations. Surface shrinkage cracks. Surface shrinkage cracks are weld discontinuities found in ferromagnetic and non-ferromagnetic welded material, most often at the weld stop and less often at the start of the welds. It is a condition where the weld loses gas coverage and porosity and rapid cooling take place. Cracks range in size from very small, tight, and shallow to open and deep. Examples include crater cracks, centerline cracks, and root cracks or toe cracks. Heat-affected zone cracking. Heat-affected zone cracking comprises cracks found in the base ferromagnetic or non-ferromagnetic metal adjacent to welds whose microstructure and physical properties have been altered and stressed, but not melted by the weld heat. This type of cracking is often quite deep and very tight and runs parallel to the weld in the heat-affected zone of the weld itself. Secondary processing discontinuities. As material moves further down the manufacturing process, discontinuities can get introduced into products due to secondary processes and finishing operations such as machining, grinding, heat treatment, and plating. Common secondary processing discontinuities include grinding cracks, heat treatment cracks, and machining tears. Grinding cracks. Grinding cracks are surface discontinuities found in both ferromagnetic and non-ferromagnetic material that appear very shallow and sharp at the root and usually appear in groups. Grinding cracks generally occur at right angles to the direction of grinding and appear to overheating, lack of coolant, rapid feed rate, or too much pressure. The image shown here is of grinding cracks located using the magnetic particle testing process. Heat treat cracks. Heat treat cracks are surface discontinuities found in ferromagnetic and non-ferromagnetic material that are usually deep and forked. However, they seldom follow a definite pattern and can run in any direction on the part. Heat treat cracks originate in areas of unequal heating or cooling due to a rapid change of material thickness and surface machining marks, fillets, nicks, and discontinuities. Heat treat cracks are serious and usually warrant an unconditional rejection of the part. Machining tears. Machining tears are surface discontinuities found in ferromagnetic and non-ferromagnetic machined material and comprise of short, jagged tears, generally at right angles to the direction of machining. Machining tears are caused by poor machining practices, such as improper or dull tools, or a lack of proper coolant. In-service discontinuities. As parts are put into service on equipment, aircraft, machinery, and so on, the cyclic stresses and environmental conditions work together to degrade the material and create discontinuities, such as cracks and corrosion. Common in-service discontinuities include, but are not limited to, fatigue cracks, hydrogen embrittlement, intergranular corrosion cracking, fillet cracks, specifically on items like bolts, thread cracks, and stress corrosion cracking, or SCC. Fatigue cracks. Fatigue cracks are surface cracks found in ferromagnetic and non-ferromagnetic material. Fatigue cracks are caused by repeated or cyclic loads that are below the yield strength of the material. They occur in regions of high stress, are perpendicular to the direction of applied stress, and are transgranular, meaning that the cracking progresses through the grains of metal rather than around them. The image we see here shown on the right is a fatigue crack located on a bridge girder. Fatigue cracks may propagate from a surface imperfection such as a pit, scratch, tool mark, or an abrupt change of cross-section. Many times a fatigue crack will propagate from a borderline or acceptable discontinuity. Once started, fatigue cracks grow rapidly and can potentially cause gross failure. Fatigue cracking is one of the leading causes of structural failure. Hydrogen embrittlement. Hydrogen embrittlement comprises surface cracks found in ferromagnetic material and are found in highly heat-treated material that has been subjected to pickling and/or plating or in material exposed to free hydrogen. This hydrogen penetrates the surface of the material, creating immediate or delayed embrittlement and cracking. Intergranular corrosion cracking. Intergranular corrosion cracking comprises surface and subsurface cracks found in non-ferromagnetic materials such as stainless steels and aluminum, but can also be found in some of the ferritic stainless steel grades and mild steel, typically in the form of exfoliation. Intergranular corrosion cracking appears as a series of small micro-openings, individually or in groups, with minimal visual evidence of corrosion on the surface. Intergranular corrosion may extend in any direction following the grain boundaries of the material. Improper stress relieving or heat treating coupled with a corrosive environment results in intergranular attack. Fillet cracks on bolts. Fillet cracks are surface cracks found in ferromagnetic and non-ferromagnetic bolts. Fillet cracks occur where a marked change in diameter occurs, such as at the head to shank conjunction, where stress risers are created. During the service life of a bolt, repeated loading takes place whereby the tensile load fluctuates in magnitude due to the operation of the mechanism. These tensile loads can cause fatigue failure starting at the point where the stress risers occur. Thread cracks. Thread cracks are ferromagnetic and non-ferromagnetic discontinuities located in the threads of a part, primarily in bolts. Cracks are transverse to the grain or transgranular, starting at the root of the thread. High cyclic stresses resulting from vibration and/or flexing act on the stress risers created by the thread roots to produce cracks. Fatigue cracks may start as fine submicroscopic discontinuities or cracks and propagate in the direction of applied stresses. Fatigue failures of this type are common. Stress corrosion cracking. Stress corrosion cracking comprises surface discontinuities of ferromagnetic and non-ferromagnetic material. Cracks range from shallow to very deep and usually follow the grain flow of the material. However, transverse cracks are also possible. 3 factors are necessary for stress corrosion cracking to occur. 1. a sustained static tensile stress. 2. The presence of a corrosive environment. And 3. The use of a material susceptible to this type of failure. In the image shown, we see stress corrosion cracking on a pipeline that was located using magnetic particle testing. For this type of magnetic particle testing, we used a white contrast background paint and visible black particles, giving us our horizontal stress corrosion cracking indications. In conclusion, NDT is typically required throughout all stages of the manufacturing process, as material progresses from a raw ore state into a finished product and placed into service. However, the level of quality at each process step is dependent on the product's final use. Knowing where to expect NDT indications, proper identification of discontinuities through the application of NDT methods, and evaluation of the discontinuities against various acceptance criteria is what makes NDT a valuable resource in all industries. And that concludes this lesson.